Okay, now we're going to continue with our review of the network layer. And next we're going to cover two more topics versus relative to the IP protocol. We just talked about the datagram format, and we spent some time talking about IPv4 addressing. The next two topics we're going to cover are ICMP and IPv6. So basically ICMP, which I'm sure a lot of you have used the ping protocol, which is use ping, which is part of the ICMP protocol, is basically a, um, a way that hosts and routers at the network layer can communicate with each other. So you can see there's a lot of different categories of ICMP messages. So basically, ICMP is used for error reporting, to report that a host is unreachable, or a network or a port or a protocol. It is used to echo a request or reply, very commonly used by ping. And basically, it's an ICMP. The ICMP message is actually above the IP datagram, just kind of the same spot where actually TCP or UDP, but it's still part of the network layer. And this is what we talked about. We said that some of these layers can be at times a little bit nebulous. And basically an ICMP message, and I do believe we're going to have a Wireshark lab that's going to demonstrate this. An ICMP message has a type and a code plus the first 8 bytes of the IP datagram causing the error. So basically you can relate the error with a datagram that was sent. So basically the traceroute command basically takes advantage of how ICMP works. So basically, when a source sends a series of UDP segments to a destination, when we use a traceroute, the first has a time to live of 1, the second has a time to live of 2, etc., etc. And it basically uses an unlikely port number. So we can basically have, whoops, I apologize, my computer has a mind of its own, and it likes to change slides on me sometimes. So this is basically, traceroute takes advantage of the fact of how these segments and packets work by sending these segments with the time to live, each one with a greater time to live. So it's going to go further and further out on the network. So for each UDP segment that it sends, the nth segment is going to arrive at the nth router. And every time the router, unless of course for security reasons it's set up to not do so, every time the router receives one of these datagrams, it discards the datagram and it sends an ICMP message with a type 11 and a code of 0. So type 11 is basically time to live expired. And the ICMP message includes the name of the router and its IP address. So basically, traceroute takes advantage of this information ICMP provides to basically provide information about all the routers along the path. Also, when the ICMP message arrives, the source records the round trip time. So This way, not only do you get information about the router, but you're also getting information about how long it took to um, traverse the router. Now, since we're using this unlikely port number, eventually the UDP segment will arrive at the destination host. Since this port number is unlikely, we're going to have an ICMP message returned back to traceroute that's going to say port unreachable with a message of type 3, code 3, which matches up with here destination port unreachable. And then finally the source stop. So basically what traceroute does is takes advantage of how ICMP error messages work to get information about the network. Of course, these days with a lot of the built-in security on a lot of these routers, sometimes traceroute basically gets blocked. So one of the problems that was basically facing us, really, we were talking about this a lot, really in like the late 90s, early 2000s, was the idea that the IPv4 addresses were going to run out. Now, of course, we have a lot of band-aids in place that we already talked about, such as using NAT and local addresses, and using DHCP, and using class-independent routing. All those things have helped the IPv4 network last a lot longer than it was anticipated. But it was felt that we had to let IPv4 and migrate to IPv6. And to be honest with you, a lot of computers do actually have support for both IPv4 and IPv6. So, but there are many that don't. So basically, IPv4 really hasn't gone away. But let's talk a little bit about IPv6. So basically, the initial motivation for IPv6 was a 32-bit address space that IPv4 was going to be expected to be completely allocated. There was also a desire to change the header format to speed processing and forwarding, and we're going to talk a little bit about that, as well also allow us to make some header changes that facilitated the use of quality of service. And quality of service has kind of been a big thing in the networking world, although a lot of it these days is actually being taken care of at the application layer, not at the lower layers, as was originally planned. So IPv6 has a longer fixed length 40-byte header, and IPv6 does not allow for fragmentation. So basically here we have the IPv6 datagram format. So it has a lot fewer basically fields in it compared to IPv4. It has obviously version, just like IPv4, starts off with version, and then after that everything is different. So version is usually IPv6 or IPv4. And it's a priority to identify the priority among datagrams and flow. It has a flow label that allows you to identify the datagrams in the same flow. This concept of flow really isn't well defined and really isn't used all that much. And then it has the next header field, which basically identifies the upper layer protocol, or it's TCP or UDP or what have you. And then it has the source and destination address, and then it has the data itself. Some other changes from IPv4 is that it got rid of the checksum. So basically the idea is we can do that checksum checking somewhere else. This basically reduces processing time, so the routers don't have to check the checksum each time. It has options, but they are allowed, but they are outside of the header. They are indicated by the next header field, so there's fewer things to check in the header by not having the options inside the header. And it has a new version of ICMP, which we're not going to really touch on, that has some additional features, including additional message types and some multicast group management functions. So these days, the hosts that are IPv6 are usually dual stack, so they support IPv4 and IPv6 simultaneously. So not all routers can be upgraded simultaneously. There's too many routers in the world that haven't been upgraded yet. You know, no one had the concept of a flag day where one day the internet was supposed to basically just, you know, change over. The internet is too big and too unwieldy for that to happen. So basically, how do networks interoperate with a mix of IPv4 and IPv6 routers? So basically what happens is the concept of tunneling is used. So basically IPv6 datagrams end up getting carried in as a payload inside of IPv4 datagrams amongst IPv4 routers. So basically you start off with a situation like this. You have a network over here and a network over here that has, you know, IPv6 capable routers, and in between them there are no IPv6 routers. In fact, in between them are some IPv4 routers, so you have to do some tunneling. So what ends up happening is you have your IPv6 datagram, and then you encapsulate it with IPv4, go through the IPv4 routers, and then you unencapsulate, and now you're back on your IPv6 network. So unfortunately, IPv6 adoption has been very slow. It's been out for 20 years, and still only 3% of industry IP routers and 11% of U.S. government routers are, you know, fully using IPv6. And I don't think that's going to change anytime soon. I think we've done a really good job of putting some band-aids on IPv4. So at least for the time being, it seems like IPv4 is going to be around for a while. Okay, now I'll take a little break and we're going to go to our final review for this learning module in regard to the networking layer.